Hi, in this video, we're going to use X-ray fluorescence imaging and analysis to study the interior structure, metal structure of a seed of Arabidopsis, a watercress plant used as a model for lots of genomic studies. Hi, I'm Matt Newville, beamline scientist at APS Sector 13 IDE, a microprobe run by the GSECARS group at the APS. We have a beamline that's dedicated to providing micron-sized beams for fluorescence spectroscopies and absorption spectroscopies and other imaging methods, especially related to X-ray fluorescence and absorption spectroscopies. We mostly do geoscience with a broad definition, including biological and plant science. So the station here is one of the stations at the APS. So that's APS Sector 13 IDE. This is a canted undulator beamline, meaning we have two undulators in the front end that we share, that hutches share these two undulators with. Actually, the undulator for our beamline only illuminates this X-ray microprobe station. So the beam comes in, so that there's a beam path here, there's metal path behind all of the equipment is a shielded beam pipe for the X-rays that go into the downstream hutches. And our beam comes from the upstream undulator with a monochromator to select a single wavelength and some mirrors to help focus the beam a little bit and to deflect the beam away. And then the entrance of our beam is down here in this lower right-hand corner of this image. We have some slits to define the beam to about 400 microns square, some attenuators and filters that we can put in the beam, a long ion chamber, just a box filled with gas with a potential across it so that some of the X-rays get absorbed by the helium, the ionized helium ions and electrons give a current that's proportional to the X-ray intensity. So we use that to monitor the X-ray intensity. And then we have focusing mirrors to focus the beam from about 400 microns down to 1 or 2 microns in size at the position where our sample sits. If I zoom in a little more, you can see in this, and if this actually works, things are a little laggy sometimes. Here you can almost see the little fiber with a sample on it. We're going to rotate the sample we're going to rotate the sample and raster it through our micro-size beam to do computed tomography. That is, we're going to reconstruct a slice through our sample that is by rastering and rotating the sample. So that's like a CAT scan, only instead of rotating the patient or rotating the detector and X-ray source around the patient, we're going to rotate the sample in the beam. And that way we'll sample every angular view of an image and can get a three-dimensional structure. We won't be doing actually 3 dimensions. We're only going to be doing one slice at a time because the beam is focused in the vertical direction. So we'll get about a 1 to 2 micron slice through our seed. If I zoom in a little bit more, you'll see the end of the fiber there with the seed on it. You can also see here, as before it zooms in, there's a microscope here and a fluorescence detector off at 90 degrees to the incident beam and in the horizontal plane. Here you can see a fiber, and just at the end of it you can see a little tip where the seed is. So again, we have a fluorescence detector to analyze the emitted X-rays from the sample, a microscope to view the sample. If I move down here, we can see the seed in about a 1 millimeter field of view on the fiber over here and extending down and the seed there. And we will spin the seed. So if I spin the seed here, you can see it rotating, and we're pretty close to the center of rotation for that seed. We'll check that, but as we rotate, we're going to rotate the seed and raster it through the beam across the beam and rotate all the way around and collect the fluorescence spectra at each of those points. We also have, if I go back up here, I'll pull out to medium zoom. We also have a downstream ion chamber. It's a little hard to see in that view or with this view. We have other detectors downstream of the beam. That's lovely. I don't know what to make of that image. It's art. I'm going to close this and try to reopen it. That's kind of cool looking. We have a downstream chamber, ion chamber as well. It's actually just under this this other camera here that has it's covered that we use that for diffraction measurements. There's a chamber that's just hidden back here that we use to measure the intensity that's attenuated by the sample. Another feature of the beam that I'd like to show you is these mirrors that focus the beam. Here, if I can get that window up, the mirrors here are flat pieces of silicon that are resting on bars, and we use those to make an ellipse. An ellipse, is, of course, is the figure that has two focal points. If you start at one focal point and bounce off the surface, you end up at the other focal point. So we're making an ellipse with one focal point being the X-ray source, 50 meters upstream, and the other focal point being the sample point, so 200 or so millimeters downstream, depending on which mirror. We have one for the horizontal and one for one to focus horizontal and one to focus the vertical separately. These are called Kirkpatrick bias or KB mirrors typically. And the way they work is there's this long piece of silicon. It's 8 millimeters thick and 200 millimeters long. Silicon is pretty stiff, but it's resting on these bars. And then we have bars on top with a little slot in the so the beam can go through. And we pull down on the top of the mirrors to curve the mirror dynamically. So we're pressing on it to curve the mirror to form an ellipse. The mirror is curved at with a radius of curvature of about 1 kilometer, so about the size of the APS itself. And you can see that there's both bare silicon and a metal coating on the mirror. The metal coating here, rhodium, which we're reflecting from now, will be able to reflect higher energy X-rays at higher energy at a bigger angle. So these mirrors are pitched to about 3 milliradians and focusing the beam by pulling down asymmetrically. Actually, if you look at how those bars across the top are pulling down, you might think that you would make not an ellipse but a parabola, and the difference is important for this application. We need to be precise enough to get more of an ellipse than a parabola. So we do two things. First, we make the mirrors be trapezoidal, not rectangular, so that we apply more force to the upstream or to the downstream end of the mirror. And also we can push down on one bar. We can push down on the bars independently. So we push down more on one than the other to help make that ellipse a better approximation of an ellipse to better focus the beam. So we have the focus beam and our sample in place, and we can now go look at the fluorescence spectra that comes off of this. We have an incident beam energy of about 11 right around 11 keV, and if I open our little shutter to prevent the sample from being hit, we see a spectrum of fluorescence. This is on a log scale. If I put that on a linear scale, does that work? We're seeing the incident beam here at 11 keV, and then we see some lower energy stuff at 10.5 or so. That's Compton scattering, so an inelastic scattering process where the free electrons are, in the approximation of a free electron, are given some momentum, often in a separate direction, and some of the energy of the X-ray is lost and scattered in not uniformly, but close to uniformly. And then we see the elements glowing or emitting as they are excited. So with the periodic table here, we can see that there's, if I click on calcium, those two lines go with calcium. There's some potassium here. And there's a lot of iron in this spot. There's iron and actually a lot of copper and what else was it? Cobalt and some zinc and some manganese in this. So there's a lot of elements in this. If I put this on a log scale, which is typical for these sorts of analysis, you can see that we actually have a good sensitivity, even at relatively low concentrations, for lots of elements. So we can see the manganese and the iron and the cobalt well for all of these elements. So we'll measure this, we'll collect and measure this spectra at fairly high rate as we go across the sample. To start with, I want to be able to rotate the sample. I showed you rotating the sample, but I want to be able to rotate the sample well and make sure that I can do a line scan across it and not do too much work. So I want to check that we're well aligned. So I'm going to make a couple of line scans as I at a few different angles. So I'm going to do a line scan at, you can see that I had just one, I'm going to do a line scan at 0 degrees and 90 degrees and 180 and 270 degrees. I don't expect you to follow like how the data collection is done here. This is more of a demonstration. But if you're interested or you want to use our beamline for this kind of work, there are instructional videos on how to use these applications to drive the beamline as well. So starting, it's going to collect data as we raster. It's collecting the fluorescent spectrum that shows up occasionally while it's collecting, and then we can look at a few different choices of what to see. So we're looking at here at the iron K alpha. Actually, as we scanned, the samples being rastered through the beam or being dragged across the beam. So we see iron K alpha is now starting to go up as we hit the sample. We can also look at the downstream ion chamber, the I1 chamber, and a little bit of a lag here as we connect with the network. It'll catch up. We can also have I1, the downstream ion chamber. We'll divide that by I0. So we see that as we go through the seed, the fluorescence goes up and the transmission through the sample goes down. And we'll use those all for figuring out where our sample is, so that we can pick a good range to do our map of theta as we go back and forth in X. So we're going to raster, again, we're going to raster the sample through the beam and rotate as we go. And we'll go back and forth and rotate at each point. So that one's nearly done. It probably is really done, and I'm going to go to 90 degrees. Scan complete. I'll go to 90 degrees and just repeat that. And I'll bring this in as we get that started. So I'll start this scan. And it's going to start going. Pretty sure it's going to start going. Hit start. There we go. So that one's going, and it's again rastering the sample through the beam. Since we're scanning directly across the beam and the beam is at the microscope is at 45 degrees, you can also see it coming in and going out of focus as we raster across the beam with this microscope at 45 degrees to it. So that'll also come up. While that's going, I'll start our application to view these line scans. See if I can get that going. And we could talk about we'll talk about fluorescence analysis when we see these, when we get the full set of scans going. So this one is also showing the drop in transmission and the increase in fluorescence. And you can see that there's like things are not uniform within that sample. Here we're doing step scanning where we're going at a half a second per point. When we actually do the full map, we'll go at 10 milliseconds per pixel, and we'll do continuous. So we'll just raster the sample through the beam and scan back and forth and rotate slowly as we go through. It'll take about an hour total of collection. Once we get it started, I'll pause for questions normally, or for a break, and then we'll record the second half where we look at the results in a separate video. So here we'll do the 180. Oh, it's going to do it again. Oh, it's just going to start it again. Okay, but this is at 180. It's incorrectly labeled. That's okay. We can remember that. So here I'm going to bring in this application up here, our viewer, to read in that data. Open data file. We had line 1, or line 0 degrees 1. That's really our 0 degree data. And we can just look at the transmission. That's our transmission chamber. We have all of these other choices of the arrays we can look at. Iron but let's look at the transmission. I think that's probably the clearest indication of where the seed is. And for now, we just have one of those. Oh no, we have the second one going as well. So we have the okay. Just a lag, a little bit of a lag. I can read in the second one. Same thing, it'll also read in the transmission, I1 over I0. We see the drop. Good. Select them all, plot them together. So these are at two different angles then, and they're pretty well aligned. I mean, there's a slight difference in the size of the seed. So that one's done. We'll go to 270, and we'll label this one correctly now. Abort. I'm going to abort that because now I'm going to label it correctly. I may have hit start too soon. $270, just so that we know. Start that one. Now it's starting that. There's a little bit of a lag just in the video feed from this while I'm recording the videos. So I'm going to read in the third one, which was labeled as 90 number 2, but it was really the one at 180 degrees. So this is a different measurement. I think we'll actually see that it's noticeably different if I select all of them and plot those together. Now we have 3, and they're pretty well aligned actually. So we can do a scan that's from maybe minus 0.1 to plus 0.2, so 300 microns across total. And that looks like it's going to be consistent with the numbers at 290 as well, or 270 as well. So we'll just pick, so this is just to help pick how big of a scan we can do. And I think we'll read this one in, but then I'm pretty sure that that's going to be okay. And we can set up our map to do to collect the full data set. So is this one almost done? That's complete. So now I'm going to read that in. Again, I think we have the answer for how we would do the scan. I'll just read this one in just for completeness. Yes. And we plot all those together. And yeah, so we can start at 0.1, maybe a little bit less than 0.1 and go a little bit more than 0.2 and we'll be good. So to set that up, we're going to go to a map scan. And here we're going to do a map where the fast direction is X. So we're going to raster the seed through the beam. Fast direction of X, actually 0.12. I will say let's do 0.125 to actually 0.15 to 2.5 is fine. And then we'll step in degrees from 0 to 360 degrees. We'll do a full rotation, and that's 400 steps in X, and that will definitely get the entire object, and we'll do 700 steps in theta. So to do this, I'm just going to, so this is a Arabidopsis seed, so I'm just going to call this a Arabidopsis seed slice 2. And then when that's ready to go, we'll hit start. Come on. Yes, slice 2, and we'll just hit start. So let's look at what this is doing while it goes. It's going to first wait, make sure the intensity is good. I can close this now. Essentially, I close the plot window. It's checked the intensity, so it's done a little bit of a dance for the intensity, and now we can watch this go. Is it rastering the sample back and forth at 0 degrees, and then it's going to step to 0.5 degree and go back the other way, and step to 1 degree and go back the other way. So it's rastering back and forth. It's done 3 rows. We have another application to read in these maps, and it's making a map, again, of X translation and theta angle. So it's rotating as it rotates the sample. So we have this other application map viewer to read in the maps, because the raw data is pretty complex for these maps. It's the full spectra from the fluorescence detector and then the transmission chamber. So the job of this program is to both display the data, but also and to help you analyze the data, including doing the tomographic reconstruction, but also to construct a single data set that is the file. So we're going to read that in and do some data processing on it as it reads it in. So I'm going to click on slice 2. You can see it starts as 1 kilobyte, and it's going to get to a few hundred megabytes of data. So there, it's read in. I hope it's looks like it's stuck. There, it's read in what, 11 rows of data. So we have 11 rows of data. So now we can plot. Let's select one of our elements of interest. So here we have all of the elements of interest, and I'll show you this in a bit as we go. So let's just pick iron. And what I mean by iron, we'll show in a bit. So here's our map of iron. In fact, if we zoom in on that, you can see that as we're rastering across, there is this very non-uniform distribution of iron there. And we can also look at another metal that I know will be interesting on this is manganese. We could replace that one, and that's the intensity of manganese. In fact, if we do a multicolor map, so let's put iron in red and manganese in green, and we'll put maybe calcium in blue, and we replace that map. Now we have a map that's all 3 colors, and you can see that they're all different. For this map, so I'll also show you that at each point in the map, I can draw a little area, draw a little blob. I'll draw a pretty big blob here, this little blob here. And this will bring up and show the full fluorescence spectrum for that area, those, 135 pixels in the map. So again, we're seeing iron, and we're seeing zinc, we're seeing our elastic line, and we're seeing the lighter elements, potassium and calcium, that are going to be in the plant. So that map's going to take about an hour, and we could talk about these analysis components while that's happening. For right now, I'm going to pause the video because it's just going to keep going for an hour. And while it's going, I will be adding more rows to the data. So if I say add more rows, this is already on. It only had 11 rows so far, and now it's going up to 30, so it'll be 10% done by the time we're done here, and or no, 5% done out of 36 out of 720 rows. And while that's going, then I can do just a replace of the map when that's done. Let's see if that comes up. Add more rows. Come on. So that's going, and we're going to, it's counting up. It should be counting up. I think it's just lagging. Rows. So while that's going, we'll just pause video and come back for the second half. That's a good start of doing X-ray fluorescence tomography on these samples. Okay, see you in the next video. Okay.